Um, homework tonight, just a fair warning again, don't wait till the last minute. The homework tonight is more optimization. We're just doing more optimization today. And have the packet handy too. Today I'm going to go through a couple more problems in that packet as well. And you'll be finishing that for homework tonight. If there are certain problems we don't get to it. So we want to make some good progress today. At least get you set up on those problems. Okay. Great. So say anything at all that can help us here, Kathy D. Like, tell us any useful information you might have. And we're actually, right now, we're all listening really carefully to you. Go. Pi r squared h. Pi r squared h is the volume of a cylinder. That was useful. Good job. Okay. Give me something else useful. Marcus. I got to find everybody here. Give me something else useful, Marcus.
Surface area equals 2 pi r squared plus 2 pi r eighth.
All right, and to get that, for those who don't maybe remember that off the top of your head, how do you? This one I kind of do remember off the top of my head. The first one, the volume one, because it's like pi r squared and then like h of them. It's like a bunch of pancakes or something, right? That kind of makes sense to me. This one maybe needs a picture. What picture are you kind of drawing to help you out there, Steven? Go ahead.
So on a cylinder, like just draw a cylinder and then.
Okay, I got it.
Yeah. So the top is pi r squared, the bottom is pi r squared.
Okay.
So if you add those together, that's where you get the 2.
That's this part. That's the top and the bottom.
And the 2 pi r height is the.
Yeah, and so the picture I might draw is like the unfolding, the net, I guess, as they say in geometry class. Right, it looks something like that when you unfold it, and then I hear what you're saying. This is pi r squared. This is pi r squared. And then this is whatever the circumference of the circle is, which is 2 pi r times, and then yeah. So I think I'm with you on this. Okay. So now it makes clear where that came from. Give me something else, anything at all useful. Maybe next step in the problem, or some other observation, or anything at all. Patricio.
You know that the volume is 1,000.
True. Good. You want to say anything else, or is that good? Is that good? All right, we'll let you off the hook. That was useful. It's true. Rosa, help us out. Anything else that's useful? Do it. Tell me what it is. H equals what?
1,000 over pi.
You got it. Wonderful. Okay. Yeah, and again, keep in mind, I mean, I think you take kind of like a easy three-step process for solving optimization. I kind of gave you some tips on Wednesday. And this is where this first tip really needs to come into play. What is it that we're optimizing is like kind of a critical question here. And it says the least amount of material. So I think we'll take that to mean like surface area. So we need to come up with an equation for that and optimize it. But that should give me something else, anything else that you want to give me that's helpful. Okay, so what am I writing? A, you mean? Got it, and of course this is what I was just kind of speaking about. I was saying, don't we want an area equation? And isn't that the thing we're going to try and find I guess in this case, the minimum of? But don't we want, if we can help it, don't we want only one independent variable? And now Vivesh has done that for us. Thank you, Vivesh. Now, you could do a little simplification work before you do any calculus as well. So some of you might have written this. What is it, 2,000 over r? Is that cool? If you simplify that? That's cool. And then take us from here. How about Kira? Give me something helpful, a helpful direction to take then. Okay, and what's the motive for taking a derivative? Okay, and yeah, what does the derivative have to do with the minimum, though? Okay, we'll take a derivative and then we'll ask the question again. Because I do like taking derivatives. You got me there. Do you want to do it actually? What would the derivative of this be? Go ahead. With respect to r. You got it. Okay, and then I'll ask you the question again. So what am I going to do with this? Like, why is that? I'm looking for. What am I looking for? What do I do with the derivative? Why is that useful? Yeah. Okay. So I'm looking for where the derivative is 0. I guess that's the observation to make, and that's like connected somehow, possibly. Not for sure, but possibly that could be an extreme value. We also, I guess, technically should consider r equals 0 because that's a place where the derivative is undefined. But I mean, in the context of the problem, I think r equals 0 is not the solution we're looking for. So I think we can safely ignore that particular critical value. But we will set this at equal to 0 and look for a place where this is 0. Christine, how'd you do on that? Did you solve that?
Yeah.
How'd you do it?
I got like solve for R.
Mm-hmm. Mm-hmm.
Shannon and I were comparing like that different answers, but I got
Okay.
Yeah.
So yeah, okay. So what was your first move? I guess I'm like talking like algebra manipulator to algebra manipulator. What'd you do? You
Multiply 4 pi R by R squared over R squared.
okay? So it's like kind of combine like terms or something like that. Okay, I'll do what you do. So you got 4 pi r cubed minus 2,000 over r squared, I guess, equals 0. And then what's the move there? What's the next move, algebraically speaking?
4 pi R cubed minus 2,000 minus 0.
Right. Yeah. In fact, some people might have made that one step and said, well, I'm just multiplying through this whole equation by r squared to clear the denominator. Right. Some of you might have done that. You all come to the same conclusion in the end. So then I think I know what she's going to do after that, and I heard a cube root in her answer that she said a second ago. Yeah, maybe we can just write it down. It's r equals the cube root of 2,000 over 4 pi. And then I guess we technically need to verify that that's a minimum too, don't we? I mean, you kind of have a hunch that since that's the only answer, and like I gave you this problem, that maybe it's a minimum, but you don't necessarily know that. I don't know. Yeah. How would you verify that's a minimum?
I think the second derivative.
Yeah, I'm a big fan of the second derivative test for extrema. You did that as an example yesterday on one. You could draw a number line too, but go ahead. So I'll take your advice.
So the second derivative of the surface area is 4 pi minus plus 4,000.
It is, and if r is positive, which in this case it is, if you plug this in, what will you get? You'll get something greater than 0 when you plug that in. So this is, in fact, concave down. The graph of a of r, this original function we were coming up with, is concave down at that point. So I think we can conclude safely that that is a minimum. And it's the only minimum we found, so it is the global minimum. Yeah.
Wait, you use like the first derivative?
Absolutely. Draw a number line. Yeah. I just think it is often true that like on a number line I might not love putting this and also I'm doing this right now, so far I haven't reached for a calculator. So like right now I'm like not a fan of maybe putting that on the number line, but like yeah, if you approximated it, it's okay to do a number line for sure. Yeah, test to the left and right. There are like a lot of hands, so let's see if we all right, go ahead. Huh? It's concave up.
Oh, okay.
Isn't it? The second derivative is positive, so it looks like this, so it's a minimum.
Alright. Oh, yeah, okay.
Yeah. So we maybe still need to, I didn't actually look at what the answer to the question is. We're not maybe done yet, but this is a minimum. This does yield a minimum. Nicholas.
Do we really need that if it's a quadratic and we already know one of the other equations is 0?
Yeah, is this a,
It doesn't apply.
is this a quadratic? I mean, you might need to tell me a little, it's not a quadratic, right? It's like a rational function, right? But I mean, you might be able to reason from the picture of this if you know what the picture of this looks like. It's just not quite a quadratic though. This guy here, the guy has a vertical asymptote at 0, for example, right? But you're right though that like sometimes you can use pre-calc knowledge to like come in and to the rescue. You're right. Yeah. Rosa, comment.
What would you do if it asked you a maximum and
Yeah. Technically, what is the maximum here? I mean, because it actually has to do with that asymptote on the graph. I mean, let's actually like think about what R values are even allowed here. That's, I think, an important question that comes up in your homework. I really wanted to highlight that today too, so we'll highlight it now. This doesn't kind of get into that, but what are the possible values for R? Do we have like a domain for this function? And by domain here, I mean a reasonable domain, right? Like R, for example, can't be negative. 'Cause it's like, in this function, if you were just saw it out in the wild, you might be like, oh, R can be negative. Well, not in our context, though. So I think we will restrict it to, and also R can't be 0, right? But can R be anything larger than 0? I think so. Anything from 0 to infinity, and then we have this point right here on it too, that we just found. So it looks like it decreases again. So some of you did the number line, didn't you? And you actually found that it decreases and then increases. It decreases, to be more precise. It decreases on the open interval 0 to this, not including 0, right? And then increases on the interval from whatever this is to infinity. So how would we maximize volume there? By the way, is there any asymptotic behavior to this? I mean, we might need a picture to help us too. I don't know. Yeah.
So you use the same ratio of radius to height, and you can just expand that based on what volume is.
I'm sorry. Maximize the amount of material.
Oh.
Sorry, did I say maximize volume? I meant maximize. I'm just trying to answer Rosa. Isn't that what you said? How would you what if the question is maximize the surface area? Isn't that what you asked? Yeah.
Like instead of using the least amount of
Yeah. So and then it's clearly not here. Like for instance, it uses more material to be like here or here, and choose an R value here or here. But I think we can choose an R value that's even better if we want more material. What are you gonna say, John?
Keep going.
Yeah, keep going this way or this way. It's hard for me to understand which direction just from this equation would be more fruitful. Yeah, I mean, I think that both of these go to infinity. I don't know how far to infinity or how close to 0 you'd have to go, but I think you can get the surface area to be arbitrarily large. Like, do you want the surface area to be like a billion centimeters squared? We can make that happen if we choose the appropriate R value. Just let R be 0.00002 or something centimeters, and then you'll have this like gigantic can with like an enormous. Can you picture it, right? Or let R be huge. Let R be just huge and let it be almost as thin as you can possibly imagine, as high as, right? You can imagine it's like this gigantic cylinder, very, very thin in height though, right? And that would be a huge way of making the surface area big too. Both extremes would produce as arbitrarily large of a surface area as you like. So it's an interesting question is here. In the homework you actually had some endpoint testing to do, and we'll highlight one of those problems. Sorry, Rebecca, you've been
Yeah,
patient.
it's,
You good?
yeah.
You sure?
Yeah, you answered my.
All right, we said a lot of stuff here. I love giving 50-cent answers to 10-cent questions. So, good. Now, did we actually answer the question yet? We actually didn't, did we? Yet? Or
We have to solve for height.
yeah, we also are supposed to give the height. So, I think it might be appropriate to give an approximation for R here. What is R? What does it come out to be? 5.42. I'll just trust you. 5.42 what? And H is approximately. Maybe you use the whole value stored in your calculator or whatever, or use like a lot. Make sure you're like rounding. Oh, by the way, maybe we should round to 3 decimal places, right? 419. Sorry, that's hard to read. And 10 point is 3 decimal places in AP. We're messing you up. That's what we're doing. 10 point. Say it one more time. 838. 83. 9. All right. Now I think we've answered the question. By the way, yeah, that's interesting. Is the radius? The radius seems to be almost exactly the height, doesn't it? I wonder if that makes me want to, as a mathematician, form a conjecture that's like always true, regardless of what the volume is. So maybe I want to, just for fun, just work this problem with a V in it, and see if we always get R and H to be exactly a multiple of 2 of each other. That's an interesting thing we could maybe try to prove. It seems to be the case, doesn't it? From this example, I don't know. All right. All right. And really, this period is for you. We can go to whatever problems you like, so I realize there's some. Let me just like mention one I like in the homework quickly, and then I do want to do some of the ones in the packet as well. In particular, I like number 2. No, I mean I do. I was gonna say there's one. The one that I was thinking of a second ago is number one. Wait, why is this? Yeah. So number 1. No, in the homework last night. Number 1, I actually like, even though it might sound really easy, because it actually made you think about the endpoints, right? Like so there you actually asked you for what is the minimum and the maximum, and so I don't really have much to say. It's not hard. I just want to draw your attention to that like sometimes endpoints need to be like in the picture as well. You need to think about like the domain, just like we did here a little bit. So if you want to talk about this some more, I can. But I just wanted to like draw your attention to the fact that that's being highlighted in number 1. Number 17 was a cylinder problem. That was fun, right? Where you're is that where you're maximizing? No, what are we doing? Is that the same problem we're just doing?
Yeah.
I feel like it's a little different. Let's see. There you're maximizing. No. I think it is basically the same thing. All right. I'm not going to do the box problem because I think we'll do that. We'll set that up right now. One of those like that here. How about this? If you'd like to see my work on one of these, I'll pass it to you. But I'd like to highlight some of the ones in the packet right now. Actually, anyone want to see my work on one of these? Thanks, Trace. You make me feel better. Yeah, yeah, make sure I get it back, of course. But, okay. You had one, by the way. I don't want to actually go through this one, but these are the problems in the packet again. I'd like to do a couple of these. Number 2, we won't set it up, but I think you had one very similar to this on the homework where you're like putting a rectangle underneath you're trying to find the maximum area of a rectangle. Something very, very similar to this problem right here, where the points are on the parabola. So maybe if we have time today, we'll set this one up too, but it does feel like one of those homework problems. I think it would be worth maybe setting this one up. Let's work through number 3, just because like the pre-calc portion of this is a little bit tricky. The thing I want to highlight and draw your attention to is this piece right here. What is the minimum cost, right? So we've got a box. I've tried to emulate that over here on the picture here. Is to have a volume of 16,000 inches cubed. The material for the top and bottom of the box is $3 per square inch, and we'll assume that like the thickness is not really an issue here. Well, the material for the sides costs $1.50 per square inch. So find the dimensions that'll lead to the minimum total cost, and also, so we're looking for both, and also find that minimum cost. So actually, give us everything. We do need, in the end, a cost equation here, don't we? But a picture would be, and I don't know what the variable will be that we'll use as an independent variable, but I'd like to come up with some kind of cost equation in terms of like the dimensions of the box. I might suggest drawing like the net again, like we were just doing a second ago. It has a top on it, right? It has a square base. That's actually a good thing for us. Right? I don't know where you want to put the top. How about we put the top right there? Can you picture that? If you unfold the box, that's what it would look like? I got to put the top somewhere. Come on, people, right? I don't know. I threw it on there. Is that cool? So when it folds up, you can put it wherever you like. Okay? You like it? All right, so now it is a square base, as I think Jonathan was noting. So let's just call, because this is math class, let's call the unknown side length here x, and then that will also be x. So that's good. In fact, all the short segments in that entire picture we could label with an x if we really want. The h, maybe we call h the height. though, for now. We don't have another good name for it. And again, every long segment in that picture, if you like, could be labeled with an H if you want. Okay, and then can you talk to me about the areas in that picture? Let's next discussion is maybe areas. So the area of this square is x squared, and so is this one. And the area of the others are all xh. So if we're now I need to think about, finally, let's not stop there, because I think a lot of people when they see this problem, they're like, okay, there's like volume to worry about, there's surface area to worry about, and in the end, the thing I actually won't need to worry about is cost. Like, so they're like kind of all these different things. This is where I was saying, give you a really good warning on that first tip in my list. Make sure you have very clear in your mind what it is you're trying to like minimize or maximize. It'd be very easy to like be like, I think I'm like maximizing volume. No. Just read the question. Okay, so can we come up with a cost equation here? It says, let's read this carefully. The material for the top and bottom of the box cost $3 per square inch. So how much together do the top and bottom cost if I know X and H? Yeah, it'll be $3 per square inch times 2x squared. So 6x squared is what? So that is saying. So that's the cost for the top and bottom. We'll put that together here. Top and bottom cost. All right, and now let's do the sides. Someone else hook us up with that. It'll be, yeah, it's $1.5, $1.50 per square inch for all the material for the sides. So help me out there. Yeah, we have 4xh is the area of all the sides, but then it's $1.50 per square inch for the sides. So this is all the sides here. Okay, so just like stare at that equation for a minute and just make sure you're comfortable with where all those numbers came from, because that was, honestly, I think that was like the heavy lifting in this problem right there. Like the conceptual work that it takes to do. Now we still have like a problem. We still have x and h in that equation. So this is where we need to kind of pull the same kind of trick we've done a couple times now, right? We do know that the volume of the box is 1,600, and the volume can be expressed simply as what? Yeah, just x squared h, right, in terms of our variables. So actually h isn't necessary to this problem. We can get rid of it, can't we? Since this is a requirement no matter what x and h's you pick, I think we can write h as 16,000 over x squared. Like again, very similar to the warm-up, except with a box instead of a cylinder. And then now we actually do have a function of only x, where x by x we mean like the side length of the box at the bottom. So, in fact, I'll leave the calculus portion to you in answering the question. Maybe we can come back around to it, but I want to set up some of the other ones and make sure we're feeling good about those. I mean, the work for the rest of this feels familiar, I think, right? So to clean this up a little bit, and take the derivative of c, take the derivative of c, set it equal to 0, figure out what the minimum cost is, what x and h need to be. Make sure in your answer, like if you're into like boxing your answers, make sure you box what x and h are, measured in inches, and also what c is given those dimensions. So box all three. I need all three of those as your like final answers, okay? Because it asks for all three in the question. I underlined. All right. So there's more work to be done, but I want to like highlight another problem here too. So again, I'm really not like emphasizing the calculus piece as much here. I want to make sure we're feeling good about the pre-calc. On number 5, I wanted to say one more thing about this, and then I'll let you do it on your own here. But we didn't really quite get to the point where we did a nice job of saying what the area of that triangle was. Remember what we're trying to do on this particular problem was we're trying to find the angle, the free choice of an angle that maximizes the area. Now I'll tell you what you don't have a free choice over, A and B. I know this can be a little confusing to see A and B in there and think, I'm not ready to take just like a derivative of this, am I? But keep in mind, like what if I gave you the following problem? I've got a triangle, side lengths 5 and 7, and the included angle is theta. And then I'd say find the angle theta that maximizes the volume. All right, good job, you did it. All right, now let's do a new problem. This time A is 27 and B is 35. Find the theta that maximizes the volume. The point I'm trying to make here is that A and B are constants in this problem, right? Theta is something that we can vary, that we can like think about the range of different outcomes that happen among a choice of free choice of theta. But A and B for any given problem that I might be thinking about are fixed. This is a pretty big idea that we'll like say a lot more about soon when we talk about related rates. But it's very important, I think, in a calculus class to think about which things are changing and which things are not changing in this equation. A and theta are like things that respond to one another. A and B are constants in this equation. So in fact, what I'm trying to say is, in fact, you can just take the derivative of this, and 1/2 A and B all just come along for the ride. So I'm taking I'm treating this as like a function. I'm treating this as like a function of theta only. And I'm taking the derivative right now with only with respect to theta. Okay? A and B are not functions of theta. So once I've said that and once you've understood it, like I think you're good for solving this, right? When is cosine 0? I think we'll yeah, now 3 pi over 2 we will allow for a triangle. But pi over 2 we'll be okay with, and hopefully that really is a maximum. Test it. But I think that does feel right. Just from the picture, that does feel right. Okay. So there's maybe a little more work to do to clean that up and make sure that that really is produces an area for us that's a maximum. But I think that's the work we want to see. And really, the heavy lifting there again is just like realizing what's going on with the problem. The derivative we just took is easy. Okay. Theta equals 5 over 2 is the answer. Yeah, but like I said, I didn't do the work of actually testing that it's a maximum. You tested it? Yeah. Let's at least set up these last two problems, maybe. At least get into them a little bit. You're designing a poster. It's probably a poster of like some famous mathematicians, maybe. I don't know. Yeah. I don't know. I don't know if I consider myself in that league there. Let's draw a more simplified picture than that, maybe. So there's like some margin around the edge. It's 50 inches squared of printed material with a 4-inch margin at the top and at the bottom and 2-inch margins at the side. I think I got it here. So what overall dimensions will minimize the amount of paper used? Okay, that's got like sort these things out here. So I definitely need some names for some variables. What would you like to? It's kind of somewhat arbitrary what we pick here, but maybe let's maybe name these outside dimensions. I don't know. X and Y. I'll go with that. Sure. L and W would be fine too. Then I think I can derive what the inside dimensions are too of this piece here. This should be, it says 2-inch margins on each side. So this should be, this distance and this distance should be X minus 4 and Y minus 8 are the inside dimensions of the printed area. Good. And the thing we're trying to actually maximize is, the area, or minimize the amount of paper used is, we're trying to minimize A equals X times Y, right? What overall dimensions X and Y will produce a minimum area? So we still need to use some of the other information here. 50 for what? For A? 50 is the area of the inside, the printed area. But it does help us a little bit to realize that. Yeah, what is 50? Let's say what that is. That's equal to X minus 4 times Y minus 8. So we're going to try and take the same approach we've done before. This is off to the side is like a constraint. It's kind of a utility equation that helps us do the thing we actually want to do over here. So what would you like to eliminate? Either one is equally easy here, right? Which one do you want to get rid of, x or y? X? Okay. All right, so I'm going to solve for x here. So I get 50 over y minus 8 plus 4. Is that what x is? Yeah? And now, I mean, I think you can see at this stage in the game, we've done this kind of move a couple times. It feels a little different here, but make a replacement up there so that you have an area of the overall poster that's just a function of y now, right? And then finish the problem. You see how these can, I mean, really, as a teacher, I always have to think, oh, do I want to expose you to like every single possible example that you could ever see of optimization? They're all so interesting and so different, right? You've seen that now in the homework. Lots of geometry and pre-calc stuff, though. So finish that problem then. And then let's at least say something about this viewing angle problem too. That's not too bad. Come on, I got you. Okay. So the picture is here. I think, did I put this picture on? No, I didn't. I don't think I put it. Did I put the picture on? Okay, good. Okay, good. So there's the picture. Very clear. I already gave you some letters to work with. This is important. The decision, if you're placing a TV screen in your movie watching room of your house, or if you're hanging, actually this is something that you might think about if you're designing an art gallery. You might want to like tell people, put the bench where the optimal viewing angle is for the thing that you're looking at, the piece of art. Or so that would be, this is what we're trying to find, is where is it true that we get the biggest theta, the most enjoyable view, the most theta, okay, on that screen. Yeah, you don't like, this is not a great place to sit, right? Not a great place to sit back here either, right? Okay. So obviously there is kind of an optimal point to sit at. So we'll take the hint. Can you write an expression for alpha? This is like trig, going right back to trig, isn't it? Give me an expression that involves the variable of interest, x. Yeah, I think tangent is going to be a strong choice here. It's definitely true that tan alpha is equal to 10 over x. And what else could you write? Similarly, tan of alpha plus theta is equal to 30 over x. So we want to maximize theta, right? So theta here is equal to inverse tangent of 30 over x minus alpha, right? And alpha is tan inverse of 10 over x. So I think we have an equation in terms of just x now, don't we? And notice along the way you're going to have to take a derivative of arctangent. Isn't that going to be fun? There's like, we have a reason for doing it. It's wonderful. And I think you'll be surprised how nicely that answer works out.